Alright guys, welcome to our Unit 6 review video. We're going to leave derivatives behind finally and move on to integrals today. That'll be pretty much the topic of our discussion for the remainder of our review time. So let's talk about antiderivatives, which is also pretty much the same thing as an indefinite integral. It's basically the process of finding the antiderivative, or the process of finding the antiderivative or indefinite integral basically is the reversal of the process of differentiation. So the integral of a derivative gives you the original function. So for instance, if x squared is our function and we take the derivative, we get 2x, right? But if you integrate 2x, then you get x squared again. So it's the reversal of the process of differentiation. All right. Now, there are a bunch of integral rules. These are great things to put on a flashcard and just commit to memory. So I would encourage you to do that. So those are a bunch of integral rules. A big type of, a really important skill when doing integration is a process known as U substitution. That's where you find an inside function and you're going to replace it with a U, right? So step one is to write out U equals the inside function. Step two is to find the derivative of that U with respect to x. Step three is to get the dx by itself. Step four is to go ahead and do your U substitution. We're going to replace the x squared minus 4 with u, and we're going to replace the dx with du over 2x. Step 5 is to simplify. At this point in the process, you should your x's should cancel out, and you end up with, it's hard to talk and write at the same time, you end up with a simpler expression that no longer has x's in it. In step 6, you go ahead and integrate like you normally would. The integral of sine is negative cosine. Don't forget your plus c. Step 7 then would be to put the u back in. My u was x squared minus 4. Okay, so that's u substitution. Sometimes it's hard to identify what your u is. Usually if you have parentheses, it's the thing in parentheses. But sometimes it can be hard. I would say the ones that are hard is like ones that are rational expressions or exponential expressions, because they don't always use parentheses on those ones. But most of the time, if you have parentheses, that's going to be your u value. Another way that you can identify what the u is instead of looking for what's in parentheses is just asking yourself, if I take the derivative of this, do I see its derivative somewhere? So for instance, the derivative of this is 2x. And so that's enough to cancel out that 2x, which is what we want. So that's another way to identify your u. Now, the next thing I'm going to show you guys is that sometimes you use long division to do integration. Long division takes a lot of work, and it's not a super important type of problem. I don't see it happen a whole lot, but it's worth mentioning. So let's go ahead and review how to do it. So basically what long division is where we're going to change the way this looks by doing some division instead. It's kind of like if you had 24 over 5, you could rewrite that as 4 and 4/5. That's kind of what we're going to be doing here. It's just that we have to do it with polynomials instead. So first of all, let's do the long division. So I'll remind you of the process here. You're going to need some room for this problem. It takes up some space, so I can erase, but you guys might want to throw this on the back of your paper or something. All right, so you ask yourself, what do I multiply x by to get x cubed? The answer is x squared, so you put that over the x squared. Next, you're going to distribute that to both of these numbers, and you're going to put them here. All right, so that would give me x cubed plus 2x squared. The next thing that you do is you subtract. So subtract and subtract. In other words, you're going to change the signs. So if they're positive, they become negative. If they're negative, they become positive. And then after that, you add down. So in this case, these cancel. And then negative 2x squared and negative 2x squared is negative 4x squared. And then you just bring the rest of it down, and then you repeat the process. So now what would I multiply x by to get negative 4x squared? And the answer is negative 4x. Multiply that times both of these. You get negative 4x squared minus 8x. Distribute a negative and thereby change the signs and then add down. These cancel. This is 5x minus 4. And we get to go one more time now. What would I multiply x by to get 5x? I would multiply it by 5. Distribute that 5 times both of those, and you get 5x plus 10. Change the signs on those two things by distributing a negative. Those cancel, and I get negative 14. And now as a result, we have the following outcome. By dividing the top by the bottom, I got this as an answer. And then I also have this as a remainder. And what do you do with your remainder? You put it over the thing that you divided by. So now this expression is the same thing as this expression. It's just been rewritten. Just a second. It's just been rewritten after having been divided. So instead of integrating this, I'm going to integrate this instead. And that's going to be a lot easier, okay? Because the integral of x squared is x cubed over 3. The integral of negative 4x is negative 2x squared. And the integral of 5 is 5x. Now the last one here, to integrate this is going to be a little bit tricky if you don't remember. Okay. I'll show you the long way and then I'll show you the short way. The long way to do it is by doing U substitution. So I'm going to show it off here on the side. Now, in this case, the U will be the denominator. Okay, so du over dx would be 1, which means that du equals dx. Then doing our U substitution, I've got negative 14 over u du. Next, I could take this negative 14 and move it outside. Anytime you have a constant multiple, you can just move it out to the front there. And this integral is a special integral. And that special integral is an ln problem. So we have the following: x cubed over 3 minus 2x squared plus 5x plus, actually it's going to be minus because of the negative 14, minus 14 ln plus c of u. And the u, once again, you want to put that u back inside. And there's your answer. Okay, so that's a long division problem, and they are long. All right, now just to give you guys some advice, anytime you're taking the integral of something that looks like this, okay, where a, b, and c are just numbers, the integral is going to be as follows. It's just a shortcut, so if it's something that you want to take the time to commit to memory, it could actually end up making things go a little bit faster for you. Okay, but there it is. Your constant goes here, but I'm not going to put c because I've already got a c and it means something else. So if I were to apply that to the problem we did a second ago, we had negative 14 over x plus 2, right? My a is 1. So it's negative 14 over 1 ln of x plus 2, and then your c. So notice how much faster that is if you know that little rule. And the only reason why you want to commit that to memory is because these types of ln problems, especially on long division type problems, These types of ln problems are very common, but they're common in other circumstances other than long division. So, all right, let's go ahead and try to take a look at another special situation in integration. So completing the square is an integration strategy that you're going to use anytime you have a trinomial on the bottom, probably a quadratic trinomial of some kind. What we're going to do is we're going to rewrite that denominator a little bit. So here's what we do. It's a weird thing to do, but maybe you'll remember it from pre-calculus or algebra 2. All right, so we're going to create a new number. And we're going to add it after the middle number here. So I'm just going to put a blank here. Then we have our 5. But since we're adding a new number, we're actually going to subtract the same number here. Because if you add a number and subtract that number, it's like you didn't do anything. And so we don't want to change the value of this expression, but we do want to change the way it looks. So we're going to add a number that we want, but we're also going to subtract it so it doesn't actually change the value of the expression. So what is this new number? Well, first of all, you take half of your middle number, which is -2, and then you square it, raise it to the second power, or multiply it by itself, and you get 4 in this case. So I'm going to add 4, but don't forget we're also going to subtract 4. All right. Now the next thing we're going to do is we're going to factor this thing here. Now, I'm going to put the answer here. If you factor it, you get x minus 2 times x minus 2. In other words, x minus 2 squared. And then you have these two, which is 1. Now, if you need help with factoring, I'll show you how I factored that really quick. X squared minus 4x plus 4. All right, so the first thing we do is we ask ourselves what times what makes x squared. That would be x times x. And what times what makes 4? Well, that would be 2 times 2, or -2 times -2. And it turns out that this is the one that would work. You can check your work by foiling. You know it's good if the outside ones and the inside ones multiplied together give you -2x and -2x, which makes -4x, which is the middle that we need. So that's how you can factor if you need to. And anytime you have two of the same thing, you could just write it as squared. All right? But that's the idea there. So let's review here. When you have an integral where there's a trinomial in the bottom and just a number on the top, you're probably going to complete the square. How do you do that? You're going to put a blank after the middle number and a blank after the last number. It's going to be the same numbers, just for the first pair you add, and for the second one you subtract. What is the new number? You take half the middle and square it. Okay. Then you factor this trinomial, and you should get a binomial squared, and you add these up. All right, so that's called completing the square. It's just a way of rewriting a quadratic. But why do we do that? Well, because it makes the integration process possible. When you do this, you always end up getting some kind of an arctangent. Okay, so let me show you what I mean. We do have a u sub problem here, right? We've got parentheses. So my u is x minus 2. The derivative of u with respect to x is 1, which means that du equals dx. So if I were to rewrite this with u substitution, it would look like this. And sure enough, that's an arctangent problem. Now when you have arctangent, you do 1 over a. The a is the square root of this number here, so that's 1. And then on the inside, you take the square root of this number, which is u, and the square root of this number, which is 1, and put them right there. Now we don't really need the 1's. So really we just have this. And then finally, we put the u back in. The u in this case is x minus 2. All right, so step 1 is to complete the square. You do that anytime you have a number on the top and a trinomial on the bottom. Step 2 is to do u substitution. Step 3 is to do your integration. All right, so that is a completing the square type of problem. Now, neither one of these problems are horribly common, but they do occur and they're worth reviewing. So I thought we would go through those real quick. All right, let's move on. Now, whenever you have a rational expression, they all look pretty much the same, but yet they do have some subtle differences, and those differences are basically what tell you which strategy to use. So, how do you tell which method to use when integrating a rational expression? For that, look at the extra handout that I posted to this assignment. For problems like, first of all, I've separated it in two kinds. I've got basic ones that look like this, and then more complicated ones, which is in part 2. So for basic ones where you have a number over an x to a power, if the power is just 1, then that's an ln problem. So the integral of this would simply be ln of x. Okay. But if you ever have 1 over x to some other power, what you're going to do is you're going to start by rewriting it as x to the negative n, and then you just do the reverse power rule. Okay, that's where you add 1 to the power and divide by that number. So there's that. Now, for more complicated looking rational expressions, we have some thoughts to go through here. So anytime the expression in the bottom's highest power is 1 more than the power in the top, it's going to be a u sub problem where you make the bottom your u. And those are typically going to turn out to be ln problems after that. Now sometimes though, instead of, if you're not dealing with polynomials, another way of finding which one is the u is so long as you see the derivative. If the derivative of the bottom is in the top, then that's also your u. So for instance, the derivative of sine is cosine, right? So since the derivative of the bottom is in the top, then that means our u is going to be the bottom. So these are u sub type problems, okay? Now, arc-trig functions, you just need to recognize their patterns. This one here is arcsine. This one here is arcsecant. And there's formulas for these. I'm not going to put the formulas on here just for the sake of time and space. It's already been put on another slide earlier anyway, but I'm just letting you know. And this one here is an arctangent. So these are things you might want to memorize what they look like. Okay? And we talked about these other two down here. If you have a trinomial in the denominator, it's probably a completing the square type of problem. Or if you have a situation where you have two polynomials that are being divided, and the polynomial in the top is greater than has a power greater than the power in the bottom, you're going to do that long division thing that we talked about. Finally, you have splitting the numerator. So if you have something like this, you could split it up so you end up with the integral of x over x and 1 over x. So you just split the numerator up, x over x and 1 over x, into two separate integrals. And that can actually make the integration process a little bit earlier. X over x is 1, and then you have 1 over x here, and that would be much easier to integrate. So all of these are rational expressions, and they all kind of look similar. They just look like a fraction with stuff in the top and stuff in the bottom, right? But these subtle differences tell you which strategy you want to use to integrate. So this is a nice reference sheet to have. Maybe turn it into some flashcards or something to help you memorize it. All right, so moving on to part B. So we've talked about antiderivatives or indefinite integrals. We're going to turn into another type of integral now called the definite integral. And it's just pretty much the fundamental theorem of calculus, which says that if you integrate a derivative, you get the antiderivative. But with numbers here, you plug them in. You plug the top one in first, the bottom one in second, and you subtract them. And basically what that ends up telling you is the area between the curve and the x-axis. If you ever have an area above the x-axis, it's positive, and if you ever have an area below, it's negative. All right? So that's what the fundamental theorem of calculus is. Now, we're going to do another u sub example, but this time we're going to do it with a definite integral. And why is that? Because you're going to see something else a little bit different happens here. And the difference is in the following thing. Don't forget to change your limits. So whenever you do u substitution with a definite integral, you have to change your limits also. It's very easy to forget about that. So step 1, find your u. Step 2, take the derivative. Step 3, get the dx by itself. Step 4, do your u substitution. I'm going to replace that with u. I'm going to replace that with du over 2. And now we get to change the limits. So this limit is going to become something. And how do you know what it becomes? You plug it in here. 2 times 3 minus 4. That would be 2. So the 3 becomes 2. To change this one, you do the same thing. You just plug it into this expression here. So 2 times 1 minus 4 is negative 2. So the limits change from 1 and 3 to negative 2 and 2. So I'm going to take this 2 out, but it is a denominator number, so when I take it out, I'm going to put it as a fraction. We have our new limits, and then we have u cubed. All right, so my u substitution is over. And so from here on over, we're just going to integrate like normal. So to integrate this, I add 1 to the power, and I divide by that value. We put the limits here, and then we're going to plug both of those in. We're going to plug in the 2, and we're going to plug in the negative 2. So this is 16 over 4, which is 4. This is also 16 over 4, which is 4. And we end up with 0 as an answer. And how can that be if this represents area? Well, if you were to graph this function, it's probably going to look something like this. Since we're going from 1 to 3 or whatever, the amount of area under the x-axis is exactly equal to the amount of area over. And so they cancel each other out and you end up with 0. So that's what that means. But that's just an extra side note. Here's what I want you guys to remember. When you do u substitution with a definite integral, don't forget to change your limits. And you do that by plugging these limits into your u equation. All right? Moving along. Properties of definite integrals. Anytime you've got a constant in your integral, you could take it out. You can only do that with constants, numbers. You can't take a variable out, but you could take a constant out. Anytime you have an integral where the top and the bottom are the same, the answer is 0. If you have an integral that's going from a to b, and if you're integrating the same function from b to c, notice that where this one leaves off at b, this one picks up at b. So you could put these together, meaning that we go from a all the way to c, and we can cut out the middleman, and we can write it like this. Okay? A way you can think about that in terms of areas, if this is a, this is b, and this is c, and here's my function. Well, the area of the first part is the integral from a to b. The area of the second part is the integral from b to c. But the area of the whole thing is the integral from a to c. Okay? That's it, but that only works if they're connected at b, right? All right, so there's that one. And then we have this property. If you have an integral from a to b, you can reverse those limits, putting the b on the bottom and the a on the top if you put a negative in the front. Okay? Here's another one over here. If you're integrating two functions being added, basically just integrate each part separately, and that's it. It doesn't work that way for multiplication. So for instance, some stuff you can't do is if you had two functions being multiplied together, that is not equal to the integral of f times the integral of g. It just doesn't work that way. Or if you have the integral of f over g, that is not equal to the integral of f over the integral of g. That's not true. You can't do that. That works for addition, but you can't do it with multiplication or division. And there might be some questions where they ask you about that in this week's work. So you want to be aware of that. This one would be a rational expression, so you would have to use one of those strategies on the how to integrate rational expression sheet I gave you. The top one here, the only way that's possible is if you can do a u substitution somehow to replace one thing with another. But anyway, I digress. These are some properties you want to have committed to memory there. All right. Integrating piecewise function is something that you might want to familiarize yourself with. So here's a piecewise function, right? And I'm being asked to find the integral from 0 to 10. So I want to go from x equals 0 to x equals 10. But what's important to notice here is that this piecewise function has two pieces. The first piece only applies to all x values less than 4, and the second piece applies to x values greater than 4. So 4 is in between 0 and 10, so I would have to split this integral up. I would have to go from 0 to 4, and that would be for the first piece up here. And then from there, I'd pick up where I left off at 4, and I would end at 10, which is where I wanted to end. So my starting point goes here, my ending point goes last, and this connection point is what goes here and here. Okay, so we're basically using that property on the last slide that I shared with you guys about. Okay, so now if I'm going from 0 to 4, which piece am I using? Well, if I'm going from 0 to 4, is that x value is less than 4 or x value is greater than 4? Which one is it? Well, if I'm going from 0 to 4, those are x values that are less than 4, so what I'm going to be integrating here is the 3. Likewise, if I'm going from 4 to 10 for this second integral, those are x values that are greater than 4, and so I'd be integrating the 2x for this piece. Okay, so that's the main thing I want you guys to be aware of when you're integrating a piecewise function, is you're going to have to split the integral up into its pieces. The first limit goes here, the last limit goes here, and where they connect is this piece here. Right, so just some stuff to keep in mind. So from here on out, the rest of the problem is really nothing new, but I'll go ahead and finish it anyway. The integral of 3 is 3x. The integral of 2x is x squared. And we just apply the fundamental theorem of calculus to each one of these. So I plug in 4, I get 12. I plug in 0, I get 0. I plug in 10, I get 100. I plug in 4, I get 16. And so I end up with 12 plus 100 minus 16, which is 90, I think it's 96 if I'm not mistaken. All right, and so there's our final answer. But all that stuff at the end is kind of like, okay, yeah, we know how to do that. This is the main thing I want to make sure that you guys know how to do, is how to split up the integral into two pieces based on the piecewise function. Next, we need to look at Riemann sums. There are 4 Riemann sums, and what these are ways to estimate an integral value, a definite integral value. Remember, what does a definite integral represent? It represents the area under a curve. Okay, but before calculus came along, what people would do is they would estimate the area under the curve by drawing rectangles. It's not a perfect fit, but it can get you pretty close. Okay, so there are 4 ways to estimate the area under the curve. Left-handed Riemann sums. That's where when you have a curve of some kind, the left edge of each rectangle touches the curve. With a right Riemann sum, that's where the right edge touches the curve. With a trapezoidal sum, that's where you draw trapezoids under the curve instead, and those are typically better estimations. And then with a midpoint sum, I'll draw that one over here. That's where the midpoint of the rectangle is on the curve. Instead of the left corner or the right corner being on the curve, the midpoint is on the curve. And so those are the 4 types of Riemann sums, which are ways to estimate area under a curve with rectangles or trapezoids. Now, when it comes to left and right-handed Riemann sums, whether it ends up being an overestimate or underestimate depends on 2 things. whether you're doing a left or right sum, and whether the function is increasing or decreasing. And this chart's pretty helpful. And quite frankly, I can't remember either. So what I always do is I just draw a picture. So if they tell me I've got an increasing function, I just draw a line like this. And if they tell me I'm doing a right-handed sum, I'll draw my rectangles from the right, and I can see from the picture, oh, it's an overestimate because the rectangles go over the curve. Okay, so that's how I do it, but if you want to put these on a flashcard to memorize it, you can. Okay, trapezoids can be overestimates and underestimates also. So if you ever have a function that's concave up, as you can see, the trapezoid goes over the curve. But if you ever have a function that's concave down, your trapezoid will be under the curve. So with concave up, trapezoidal estimates will give you an overestimate. And with concave down, trapezoids will give you an underestimate. So we're going to do an example of one of each of these things now. So let's begin. So I want to estimate this integral, given that my function is x squared minus 4. All right, now you want to pay attention to how many subintervals they want. So step 1 is you find your subintervals. How do you do that? You take your last number, you subtract from it your first number, and you divide by the number of subintervals. So that's going to be 10 minus a negative 2 over 4, which is 3. And that means your subintervals are going to be 3 units long. Okay? So that tells me how to make my table. We're going to have some x values, and we're going to have the output values here. So we start at negative 2. And then we go up by 3's after that. So if I add 3, I get to 1. And if I add 3 to that, I get 4. Now, why am I adding 3? Because that's this number here. And we just keep doing that until we get up to the number that we want, which is 10. So I stop. We're going from negative 2 to 10. And as you guys can see here, we should have 4 subintervals now that are equally spaced. So from here to here is 3. From here to here is 3. From here to here is 3. And from here to here is 3. All right? Now step 3 is you need to find your y values, your output values. And you get that simply by plugging them into this equation up here. So if you do negative 2 squared minus 4, you get 0. If you plug in 1, you get negative 3. If you plug in 4, you get 12. And so on. 49 minus 4 is 45. And then 100 minus 4 is 96. So those are huge numbers. All right, there's that. All right, now the next thing that we do for step 4 is we do the sum. Okay, now the sum depends on what kind of Riemann sum you're doing. So for a right Riemann sum, we start on the right side and we multiply it times the base. So what the bottom number represents is the height of your rectangle. And what these subintervals represent are the bases. And so the height of each rectangle will be what's in the y column. The bases will all be 3. So my sum will be 96 times 3 plus 45 times 3 plus 12 times 3 plus negative 3 times 3. And we won't use the last number. Okay? And then you add all those up and you have your answer. So let's review the steps here. That was a right Riemann sum. Find your subintervals, last minus first divided by the number of intervals you want. And that tells you how big your bases are. Make your table. Start with the bottom number, end with the top number, going by whatever your subinterval bases were. Find your y values by plugging those into the function, and then do height times base, starting from the right if it's a right Riemann sum. Now we could do the same thing again, just for more practice here, with a left Riemann sum. Our whole table is going to be the same. So steps 1, 2, and 3 will all be the same because I'm still using the same function. I'm still going from -2 to 10, and I'm still doing 4 subintervals, so I'm still going to get the same table. So let's go ahead and draw that out. We're starting at -2, going up by 3s, and then we plug in all right. The only difference for a left Riemann sum is that we start on the left side. So now these are my heights, and my bases are still 3. So base times height, base times height, and so on. And just like with the right Riemann sum, we left out the left last point. When you're doing a left Riemann sum, you leave out the right last point. Okay, and so that would give you your estimate under the curve using 4 rectangles that each have a base of 3, and their corners touch their left. This should say left, by the way, that's a typo. Their left corners are touching the curve, and these would be the heights of those rectangles. So base times height, add it all up, would give me the estimated area under the curve. All right, let's go ahead and take a look at a midpoint sum. Midpoint sums are a little bit trickier to do. And the reason for that is when you get to that third and fourth, well, the third step, where you have to find the midpoint. Okay, so let's look at step 1. Step 1 is still last minus first over 4. So the last number minus the first number over the number of subintervals is still 3. So we still have 3 there. Next, we go ahead and we do our, I guess, is this the step where we do the table? I think it is. Now this is the part where we have to get a little bit creative, okay? I'm going to start at -2. Then my next number, if I go up 3, is going to be 1, right? But I'm going to leave a blank in between them this time. Then we go up by 3 again to find the next number, which is 4. Then we go up by 3 again to find the next number. And then we go up by 3 again to find the last number. So we're going by 3s every time, right? So nothing's really different, except I'm leaving space between each number, because what we really want is the number between these. So what number is in between -2 and 1? Well, if you don't know how to do that, basically what you're going to do is you're going to add these numbers together. Let me back up. Add those numbers together, like -2 and 1, and divide it by 2. So that's -1 over 2, which is -0.5. So we're plugging in -0.5. Okay, that's the one that we're going to use to get our height. We don't really care about these heights. These are the corner points. We want the midpoints of each rectangle. So we need to find the midpoints. So let's review so far the difference, because after this it'll all be the same. You still find your subintervals. You still go by 3s, but when you make your table, you leave a space between each one, and you're going to find the midpoint of each pair. Okay? And those are what we're going to plug in to find our y values. So let's find the next one. What's the midpoint between 1 and 4? Well, 4 plus 1 over 2 would be 2.5. And so the midpoint here will be 2.5. And we're just going to keep doing that. The next one will be 5.5, and the next one will be 8.5. Okay? And those are the ones that we're going to plug in to find the y values. We're not going to plug in the red numbers. We're going to plug in these purple numbers. Okay? So let's see. I'm going to plug 0.5 in first. That's 0.25. And so if I subtract from that 4, I'm going to get -3.75 for my height. -3.75. And we're just going to keep doing that. But I'll just fill the rest of them in real quick to save time. And there's that. And then in the That's the third step technically. And the fourth step, you go ahead and find your sum. So it's going to be 3 times negative 3.75 plus 3 times 2.25 plus 3 times 26.25 plus 3 times 68.25. And you don't leave any of them out this time. You do all of them. So base times height, base and height, and so on. All right, and just add them all up, and that's it. All right, and then we have one more, a trapezoid sum. All right, our last one is the trapezoidal sum, and the first few steps are all the same thing. You still find the subintervals by doing last minus first divided by the number of subintervals. You still set up your table and find the y value, so let me bring that on up here. But what does become different at this point is how you calculate the areas. The formula for the area of a trapezoid is the height over the base, the height over 2, not the base, multiplied by the sum of the bases. Okay, so this one's a little bit reversed. The bases are on the bottom, actually. So these are my bases for the first trapezoid. And then the height is the distance between these, which once again is 3. So my first trapezoid area would be calculated like this. Height over 2 times the sum of the bases. Then your next trapezoid will be the same process. So now my next pair of bases will be this with a height of 3. So that would be 3 over 2 once again, and negative 3 plus 12. And we just kind of keep doing that repeatedly until we get to the end. So for the next pair, it'll be height over 2 times the sum of the bases. And then finally, height over 2 times the sum of the bases. Okay, and when you're all done finding each one of those things, which I'm not going to take the time to do because we all know how to do that, you just add all those up to get your answer. Okay, so that's it. That's the trapezoidal sum. All right, moving along here. Let's talk about accumulation functions. This is our last topic. An accumulation function is where you have a definite integral, but your limits are functions themselves. Okay, so there's that. Now, it's also called an integral function. Now, the second fundamental theorem of calculus is this. If you have, this is the base, I'm going to give you a basic version and a more complicated version. The basic version is this. If you have just a number down here and just an x here, then if you take the derivative of an integral, basically the derivative and the integral cancel each other out, but in the process the x drops down inside, so you end up with this. That's it. So the derivative cancels the integral and the x drops down inside and you get that. So let me show you an example of something like that. If I had the integral from 5 to x of e to the x, e to the t dt, and I want to find the derivative of that with respect to x, this and this cancel, the x drops down in the place of the t, and I get e to the x is my answer, and I'm done. Okay, that's the second fundamental theorem of calculus. Now you can work it out the long way, where you actually integrate this and plug these numbers in and subtract them, but you're going to get the same answer. So it's just a shortcut. Now, there's a more abstract version of that, though, for situations where you don't have just a number and just an x. So in those cases, if you have a function down here and or a function up here, then the derivative is going to be a little bit more complicated. So you can kind of still think of this as the derivative canceling out the integral, so you just get the function again. But since you have two different things now, you get the function with the g plugged in, and you also get the function with the a plugged in. So you're going to plug both of these in and subtract them, right? Now, why is there a G prime here and an A prime here? Well, it's basically because of the chain rule. The derivative of this is G prime, and the derivative of this is A prime. So that's the process. You're taking the derivative of a composite function. When you do that, you have to multiply by the derivative of the inside. So for these types of problems, you're going to drop this in, and you're going to drop this in, and then you multiply each one by the derivative of the inside. So there's that. So if you were doing an integral like this, let's say you had x squared here and 2x here and sine x here. Okay, well, you're going to do sine x, and you're going to put the 2x in first, and then you're going to do sine, and you're going to put the x squared in next, plus in the middle, but we also need to multiply these by the derivative of the inside. So this one will be 2, and this one will be 2x. And so that would be the derivative of that integral function. So that's your second fundamental theorem of calculus. Okay, you will see some problems like that. The last slide is basically just kind of like a really common type of question. These are really big FRQ type questions, so I just wanted to go over one of these with you guys, and that way you can just have an example on hand to look at as you're preparing for the test here. So given below is a graph of f prime of x, and also we know that f of 3 equals 4. Now this is what we call an initial condition. I'll abbreviate that IC here. And f prime, that's my graph. Okay, so keep those things in mind, and let's go ahead and begin. So the first question that we have here says, write an integral function f of x. Well, to write an integral function that gives me f of x is equal to the starting amount, which the starting amount they give me is 3, so I'm going to go with that. The starting amount plus the integral from 3, that's where we started, right, up to any number we want to, x, of the derivative. So this is a lot like our rate in, rate out type of questions here. It's just that there's only one derivative. So you have your starting amount plus your net change gives you the total amount, basically, right? The trick here is you want to make sure that this number and this number match, and those numbers come from here. Okay, so there's our integral function. I'm going to erase this as I go because I don't have space, but you guys can maybe squish yours on the back page. But that's the integral function. So basically, if you have a, this should say f prime, by the way. If you ever have a derivative graph, you can write a function that will give you the original graph, or the original function, if you will, by writing out that formula the way I just showed you. All right. Find f of 0. So what would f of 0 be? Well, f of 0 would be f of 3 plus the integral from 3 to 0 of my derivative. Now, we know what this is. They told us that. F of 3 is 4. Now, you guys notice something funny about this integral? The numbers are backwards, 0 and 3. 3 should be on the top and 0 on the bottom. So I'm going to change this to a negative so I can switch those around. That's one of my integral properties there. Now what this is this is the area under the curve. Okay, so from 0 to 3, I want to find the area of this shape. Now that's a trapezoid. So the base is 1, and this base down here is 3, and the height is 2. So the area of a trapezoid is height divided by 2 times the sum of the bases. And so I get 4. So I have f of 0 is 4 minus 4, which is 0. All right? So I started off with finding an integral function because that's really helpful for answering questions like that. Okay? Let's move along. Question number 3, they want me to do the same thing now, but with f of 5. So I want to find f of 5. F of 5 is going to be the starting amount that they gave me, plus the integral from 3 up to the number we want, which is 5. Now we already know this is 4. They told us that. Now I want to find the area under the curve from 3 to 5. That's from here to here. And that's another trapezoid. So the base is 1 and 2 with a height of 2. So height divided by 2 times the sum of the bases. And that's 3. And so this answer will be 7. You'll notice this time I didn't change this to a negative because I didn't need to flip these. They were in the right order already. All right, let's go ahead and take a look at number 4. Now we want to find f prime of 5. Now, that's actually really easy because this is the graph of f prime. So all we have to do is go over to where where x equals 5, that's right here, and find the y value at that point. As you can see, it's right on the x-axis, so that would be 0. Now, another way you could do it, although it's a lot more difficult, is you could take your little expression that we created back on number 1, and you could find the derivative of that. So f prime then would be the derivative of 4, which is 0, so that just goes away. And then the derivative of this, which is the second fundamental theorem of calculus, these cancel and this drops inside, and you just get f prime of x. So as you can see, that's not very helpful, but the point is that we want to look at our graph. All right, let's go ahead and move on to number 5. Let's find f double prime of 5. All right, so for this one, I would add a little note here. F double prime of x is the slope of f prime. In other words, it's the slope of our graph. So I want to find where 5 is at on my curve, and I want to find the slope of that line. Okay, so what is the slope of that line? Well, at this point, I'm at 0. Well, that's not right. It's 5, 0. And at this point, I'm at 6, negative 2. So we have to figure out our rise and run here. How far down did I go? I went down 2. How far over did I go? I went over 1. So rise over run would be negative 2. And so the answer, number 5, is negative 2. So for these guys here, if you want to find the original function, you need to use an integral function to do that, and you're basically finding area under a curve. To answer problems about the graph itself, just find the dot on the graph and give the y value that goes there. To find the derivative of this derivative graph, you're looking at the slope. All right, let's go ahead and move on to number 6. When is f increasing? All right, so f increases. Now I gave you a little chart for this a few slides back. F increases when f prime is greater than 0. In other words, above the x-axis. So this chart here is above the x-axis here. And so my answer to this question then would be on the interval from 0 to 5. We can also talk about when it's decreasing. That's just the opposite, obviously, right? So, and I would encourage you guys to write the reason that I'm writing here, because if you have an FRQ question, this is how you'd have to write it. F is decreasing when f prime is less than 0. And that happens on the interval from 5 to 8. In other words, it's below the x-axis. What are the critical values of f? Critical values happen where critical values occur when f prime equals 0 or f prime is undefined. Okay, well, this is a graph of f prime, and as you can see, there's really no places where it doesn't exist. It's a continuous line, so we don't care about that one. But there are some places where my first derivative equals 0, and that's anywhere it touches the x-axis, so here and here. And we're all done. What are the relative extrema of f? Well, if you look back at that chart that I gave you a little while back, f has a relative max when f prime changes from positive to negative. This happens at where? Here we're going from above to below, and that happens at 5. So we would say at x equals 5, we have a relative max. Now, if they wanted to ask you what the actual max is, the max happens at 5, but that's not the maximum value. The maximum value is the f function's value at that point, which we already found earlier. What did we find that out to be? I think it was like 7 or something, if I recall right. So that's the maximum value of your function. All right, so we also might want to find some relative minima. Now, relative mins occur when f prime changes from negative to positive. In other words, from below the x-axis to above, but that just doesn't happen anywhere. It almost happened here. It was below, but it never really made it to going above. So 8 would have been a relative minimum, but it didn't make it. And so we would just say this does not occur. Okay, so those are our relative extrema. That's another type of question I'll ask with these types of questions. Next, they're asking, when is f concave up? Well, f is concave up when f double prime is greater than 0. Now, f double prime, remember, that's the slope of this graph over here. So f double prime is greater than 0. In other words, positive anytime you have a positive slope here. So here, f prime has a positive slope, and here, f prime has a positive slope. So this occurs on the following intervals, from 0 to 2, as well as 6 to 8. Right? The next question is probably going to be concave down. It's just the opposite though, right? So when is f concave down? Well, that's whenever the graph has a negative slope. So that would be here. There's only one place where that occurs. So f is concave down when f double prime is negative. This happens on the interval 4 to 6. All right, next question. Where does f have a point of inflection? F has a point of inflection when f double prime changes signs. In other words, whenever the concavity changes. That's what a point of inflection is. That's the point where the concavity changes. So if f double prime is changing signs, that means that the concavity is changing. Okay, so where does that occur? Well, that happens anytime we go from a positive slope to a negative slope or vice versa. So here we go from positive to 0, so that's no good. But here we go from negative to positive. And so we really only have one point of inflection here, and it's at 6. So this happens at x equals 6. And there you go. What are the absolute minimums and maximum values of f? Well, anytime you want to do an absolute min or max, you're going to make a chart. Your x values go here, and the function you're trying to find the max of goes there. You include the endpoints, which are 0 and 8, and you also include the critical values. Those are the places where it touches the x-axis. So I'll title these ones EP for endpoints. Critical values, those are places where the first derivative is 0. This is the first derivative, so it equals 0 when it touches the x-axis, so that's at 5. Now we've already done a lot of these things. We've already found f of 0. We did that back on number 2. And we found out that that was equal to 0, I believe. Let me make sure I forgot. Recalculate that. Yeah, so that was 0. And then f of 5, we actually found that one already too, back on number 3. That one came out to be 7. And then the only other one we need to find now is f of 8. And you're going to find f of 8 the same way we found 0 and 5. So f of 8 is equal to f of 3 plus the integral from 3 to 8. So this is 4, and this is the area from 3 to 8. So we need to find the area of that trapezoid, and we need to find the area of this triangle. All right, so the first trapezoid there has an area of 2 plus 1 is 3. And then this one here, this triangle, has a base of 3 and a height of -2, so that's -6. That's -3. Notice I said it's negative because it's below the x-axis. And so in that case, the total area is putting these together, so you end up with 0, which is 4. And so as you guys can see here, this is my absolute minimum, and this is my absolute maximum. And that's how you find absolute mins and absolute maxes. And that's it, guys. So that's the end of this one. Sorry that was a long one. It happens, but anyway, we'll see you guys in class.